Okay, so yes, chapter 15 on its face looks really, really hard, right? But I'm hoping today we can make it a little bit easier. Okay. Okay, so kinetics is study of chemical reaction rates. And so anytime we have a rate measurement, let's not even think just about chemistry, but like anytime you're talking about a rate, like miles per hour is a rate, right? It's the units that are changing divided by the time, right? So for kinetics, it's the same thing, right? It's divided by time on the bottom, and the units that are changing is going to be the concentration of, in this first case, it's C, which is one of your products, okay? So this one, there's two equations that the book gives you, and the key thing to remember is that this one, thought I turned on my pen, is products. Yes.
Is it on the sheet or not?
It does not say product on your sheet, but it does give you the given, okay? So you have the given. A chemical reaction is A plus B react to form C plus D, right? And so this C here is on the product side, okay? It could be D, right? It's any of the products. It could be C or D, but it's written in your book as C, okay? Now the brackets that are like this means concentration of. Concentration.
So it's not like multiplier?
It's not a multiplier. I mean, no. It's so, and we know delta means change in, right? And so all of the symbols is change in concentration of C. Okay? So that just means you're going to do a subtraction problem up top with one C concentration and then the other C concentration. And on the bottom, you're going to do another subtraction problem. This little t is time, right? So it's a difference than big T, because big T is temperature, right? So you're just doing the change in the concentration of one of your products divided by the time, the change in time over the same period. Okay, so I already told you that. The units, so the concentration is going to be measured in big M, which is molarity. Right, yeah. We're going to, molality is just like this tiny, tiny part that we use it, and then everything else is molarity. Okay, so units are big M, molarity, and then time is going to be most of the time in seconds. For everything in our purposes, it's going to be molarity over seconds. Okay, we're not going to switch it up. Okay, now, if you don't know how the concentration of the product is changing, but you do know how the concentration of the reactant is changing, you can still use this equation, but you just have to modify it. Because let's think about when we're doing a reaction. What happens to the concentration of the reactants over time? Increase or decrease?
Increase.
Increase. So you have added one mole of salt and 1 mole of chloride to try to make sodium chloride, and 5 minutes later, is there more or less sodium than when I started? Decreased, right?
Adding different.
And so your reactants always decrease, okay? And your products always increase, right? And so when we are doing the rate, we're trying to find the rate for the rate is a positive measure, okay? And so the products, having this first reaction here, it shows that. It's a positive measure. What is the rate of creation of the product is what we're measuring. Okay, but if we only have the reactant, that rate is going to be negative if we don't do something to it, okay, because the concentration is going to decrease over time. And so we just add a negative symbol in front of the change in the concentration of the reactant so that the rate will be positive.
So we would
Okay.
write that number as a negative.
Yes, because this number, this delta A, will be a negative number.
It'll already be negative.
It will be a negative number, but you want the result to be positive.
Right.
And so you're going to multiply it times
Okay.
-1 to get it to be positive. And they're inverse, right? They're directly inverse. As the reactants decrease, the products are increasing at the same rate. They're like an X, like this, okay? And so by just changing the sign, it's basically all you're doing is changing the sign so that it's positive. When you do the rate with the reactant, you're making it exactly as if you measured the concentration of the product, okay? So you do have both of these on your facts and formulas sheet. You just need to know which one to use when, okay? If we're asking you for a rate and I've only given you a concentration of a reactant, then you have to use the second one with the A. If I'm asking you for a rate and I've given you the product, then you use the first one that has the product in it, okay? I mean, and it's just, you're also given this, so just look, okay, I've given C, so I'm going to use the C one. I'm given A, so I'm going to use the A one, okay? Okay, so first little problem here. So this reaction rate, it's kind of funny because everything else, like we call it an equation, and this looks like an equation, but we call it a definition, okay? Because we actually have a different reaction rate equation that we use later in this first half of the chapter, okay? So if I ask you for the definition of reaction rate in terms of this, I'm asking you for what is the equation on your facts and formulas sheet, but making it in terms of this. So it's going to be rate equals, okay? And then I'm going to look at what it's asking for. So NH3, is that a reactant or a product? Reactant, okay, so that's an A, right? And so I'm going to use the negative delta, and in place of A, because it's asking me in terms of, I'm going to put in the NH3, okay? So negative, change in the concentration of NH3, ammonia, divided by, and I haven't been given anything else, so I don't have to plug in anything else on this. It's just delta T. So this is the definition
So
here.
Is that the answer then?
This is the answer. Yeah. Now if I actually gave you values, you'd plug in the values, right?
So
But if I'm asking you for the definition of the reaction rate, this is what the answer looks like. Okay? This is kind of a hint because there's a weird question that asks it in just this way on the exam. So, Janet, there's a. Yeah. Okay, so then for the second one, definition of the reaction rate in terms of another one. So we're going to write it rate equals, okay, and so I'm going to look at this, and is it a reactant or product? Product. And so I'm going to use the delta C one that has the product in the reaction or in the definition. So delta, oops, I put C here, but so we're not going to put C though, and it's also changing the concentration of C. So we're going to put change in concentration of, and then I'm going to put this whole thing in H4 NO3 because it's asking me in terms of, so that means it wants me to put that, like insert that thing into the equation. Divided by delta T. And make sure you use the lowercase t on that because uppercase T means something totally different. So that's the simplest part of the first half of the chapter. Okay, but what affects the reaction rate? Let's just talk about that for a second. Okay, so the higher the concentration, the faster the reaction is going to proceed. The greater the surface area, so think about our Tums experiment, right? The faster the reaction will proceed because it's almost the same thing as increasing the concentration, right? It increases the available concentration of our reactants to react with each other. And then temperature, the higher the temperature, the reaction will be faster also. Okay, and all of this is because of collision theory, okay? And that theory states that in order for a reaction to occur, the reactants must collide with each other in just the right way, okay? So let's say I have this reactant that looks like this, okay? This reactant that looks like this. And if it hits here, it doesn't react. If it hits here, it doesn't react. If it hits here, it does, okay? So it has to collide in just the right way and with just the right amount of force, okay? And that's called an effective collision. There can be lots of ineffective collisions that don't do anything, but if I do this, it turns into something else, okay?
So is that like with a battery, if it's not in the right way, it won't work?
I mean, I guess that would be completely ineffective because it can't even reach each other. I don't know. It's kind of an apples and oranges comparison. Okay, so if we think about this in terms of these collisions, that means if we increase the concentration, if there are lots more of all of the reactants and they're in like liquid form or gaseous form, right? And they're going all over the place, the more there are, the more chances that we have effective collisions, right? Because there's just more of them that are able to collide, okay? Again, same thing. If we increase the surface area, it's effectively kind of increasing the concentration of available reactants. It increases the chance of a collision, okay? And also, finally, if we increase the temperature, what happens if we increase the temperature? Why would that increase our chances of collision?
Because it becomes like a gaseous state. Because it goes into a gas state eventually.
Well, even if we stay in the same state, say we're staying in liquid state, but we're increasing the temperature, what's going to happen? That would increase the chances of an effective collision.
Is it the molecules bouncing around everywhere?
Yes, they're moving faster, right? And so that increases the chance of an effective collision. There's more chances over the same amount of time that they'll hit each other correctly, okay? And so that's collision theory. And so you should know that each of these things increase the chances of collision. Now, the more collisions we have in a certain amount of time, what is happening to the rate of the reaction? Increasing or decreasing? Increasing, okay? And I just gave you an example of a rate definition, right? Collisions over time, right? And the more collisions over time, the more product you're creating, the more concentration of that product is increasing and over time, okay? So all of these things increase the chance of collision and therefore increase the rate of the reaction.
Mom, we need our waters.
Well, get them. Okay. So, change in reaction rate over time. So we already talked about how the concentration of the reactants will always decrease as the reaction is progressing. Okay? And therefore, from what we just talked about in the last slide, if we reduce the concentration, that slows down the reaction because fewer collisions will occur. So, if we are starting with a concentration up here, and it's naturally going down over time because the reaction is happening and those reactants are getting used up, what's happening to the reaction rate over time?
Slows down.
It's slowing down also, okay? Because at the beginning of the reaction, you had a high concentration, and at the end, and by the end of a reaction, you have a very low concentration, and so it's slowed down to almost nothing, okay? So, reactions will always slow down over time. The very beginning, when the reaction starts, is the fastest it's ever going to be. The end, it will be almost zero concentration change, 0 molarity per second, okay? Okay, so now we get into the rate equation. I wish he used a different term for this instead of equation, because nobody else uses this term. So like all the YouTube videos that are on the YouTube channel, they call it the rate law, okay? And so I'm going to use rate equation because I'm staying consistent with the book, but just so you know, if you're in chemistry in the future, it's called the rate law. Okay, and so every reaction at every temperature has a different rate law, okay? It changes depending on exactly what the reaction is and what the temperature is. But you can still fill in these things here, okay? So rate equals a K, the K stands for constant, and we had to use K because C is being used for something else, I guess maybe from physics, speed of light, but K, so we had to use the next best thing that starts with a K sound, and K is constant, okay? And so that K is what will be different for every reaction and temperature, okay? And not only will the number be different, but the units will be different. But you can figure out what the units are based on the other things, which we'll learn, okay? So within the brackets, the same thing as before. When you have those special square type brackets, that means concentration of, okay? And I know, like I talked with you, Elijah, last week about chapter 14, and you're like, it's so hard. And I was like, no, it's easy. And I think a lot of it is, we're used to reading things in English. And when all of a sudden we're having to read things in symbols, your brain just goes, wah, right? And so that is a lot of this, of 14 and 15, is getting the symbols down, being able to just see the symbol and say, oh, that is constant times concentration of A, right? Okay, so X and Y are the orders, which sounds so complicated, and it's not, and I'm gonna hopefully show you that, okay? The word orders, to me, when I see orders, I think sequence, right? It's not sequence at all. It's not sequence, okay? So all it is exponents. And we've used this fancy word order, okay? So it is the concentration, or the constant times A, the concentration of A to the X power. It's an exponent, times the concentration of B to the Y power, okay? Now, if you have more than 2 reactants, you would continue writing. So if I have a third reactant, I'm going to have C here and put it to the Z power, for example. Okay, you would put all the reactants and are included in the rate. Now, why do we have this X, Y exponents thing? Okay, that is because depending on the reactant, I guess they're better at those collisions, okay? And so that concentration will increase by an exponential, increase the rate by an exponential value, potentially, depending on what the reactant is, okay? So, continuing with this strange language orders, okay? All it means is to the whatever power, okay? So a 0 order reactant means that concentration is written in that rate law equation to the 0 power, okay? Now, anything to the 0 power, I didn't mean to put all this up on the screen at once, y'all, but it is. So anything to the 0 power is 1, right? So we could technically not even write that one. Like we wouldn't have to write the brackets with the concentration of X or A, whatever, because it's just multiplying the whole thing times 1, right? What that means is that the concentration of that reaction has no effect on the rate of the reaction, okay? It doesn't matter how much vinegar I add to my baking soda. I don't know what the reaction orders are on those, but the reaction will proceed at the same rate, okay? Or what concentration, shouldn't say how much, what concentration of vinegar, if the reaction will proceed at the same rate, okay? A first order means that that concentration is to the 1 power in the reaction rate equation, and you wouldn't have to technically write the 1, right? Because we don't usually write exponents of 1. And anything to the 1 power is itself. So what that means is that when we put it in this, let's write this equation, rate equals K times concentration of A to the X concentration of B to the Y. Okay, so let's look at A, okay? If A to the 1 power, that means that the rate will increase very directly by what the concentration is. So if the concentration doubles, the rate's going to double, right? If the concentration of A changed from 1 molar to 2 molar, the rate's going to double, okay? If it tripled, then the rate would triple, right? Second order means that the concentrations to this 2 power are squared. And so how that's going to affect the reaction rate is if the concentration doubles, the reaction rate is going to go up by 2 to the 2 or 4 times. Okay, so the concentration doubles, but the rate goes up 4 times as fast. Okay, tripled would go up 9 times as fast, 3 to the 2 power. Okay, all right. Third order, we get a lot fewer of those, but third order would mean that it is to the 3 power, or it's cubed. Okay, so if we doubled the concentration, if we went from 1 to 2 molar, then the rate would go up 8 times as fast. Okay, and so what here is like what I'm doing to the change in concentration when I put this 2 here. So 2 is the change in concentration, and then to the 3 power. So it'll be 8 times as fast. Okay, if we tripled it, it would be 3 to the 3 power, or 27 times as fast. Okay. Now, final thing, the easiest part of this whole thing, the overall order, the easiest one to figure out, it's just the reaction concentrations added together. So it's X plus Y. Okay.
Do we need a why? Okay. So we just add those together if it asks for the overall order.
Yes. Yeah. Okay, well, here's practice. So we have a reaction. We're given the rate equation here. We don't know the constant yet, but we're just being asked about the orders, okay? So in this particular rate equation, what is the order of the reaction with respect to reaction HNO3? So
What is with respect to?
it means looking at just that one's order. How is that one affecting the reaction?
Paying attention only to that one.
Yeah. Okay. So reactant HNO3, what's the order? What's the exponent? What? Exponent's going to be a superscript, right? So what's the exponent here?
Oh, 0.
No. If it was 0, I wouldn't write HNO3 at all, because if I put if I put HNO3 to the 0 power, it doesn't matter what number it actually is in HNO3. It doesn't matter what that concentration is. The numerical value of that is 1, right?
Okay.
But
So we could just rewrite that as 1. That whole part.
this, if it was to the 0 power, or just not write it at all, because you don't need to write a 1 times anything. Okay. So if it's written there, then, and it doesn't have a 0 next to it, it has something besides 0. Okay. So
Why would it have a 0 next to it, like a 0 time? Because I mean, you had that on the screen.
I mean, you could technically write it in there and put a 0. It's kind of a redundant thing because it's 1, right? So, but if it's written there and it doesn't have any exponent at all, then it's the one exponent that you don't have to write and have it there. Have the bottom part there. And so it's going to be 1. Okay? So 1. It's the order of the reaction with respect to reactant HNO3. Okay? Same question for NH3. What is the order? 1 again, right? Exponent, if it's unwritten, nothing there, it's 1. Okay. And then there, what is the overall order? Well, you had a 1 here and a 1 here, so it's 1 plus 1 is 2. Okay. Now, new part here. What is the unit of the rate constant? Okay, so to teach you that, I'm going to write this rate equation out, but I'm just going to put units, actually. Let me undo that. Okay, so what are the units of rate?
Molarity over seconds.
Yes, molarity over seconds equals, okay? Our K is what we don't know yet, okay? That's what it's asking. What is the unit of the rate constant? Okay, what is the unit of my concentration of HNO3? What do we measure? What units are we measuring concentration in?
Molarity.
Molarity. Okay, and there's to the 1 power, so not going to write any exponents. And then what is NH3 units? Concentration. Also molarity. Okay, so to get K by itself, it's going to be molarity divided by seconds times molarity times molarity, right? I'm putting dividing by both of these equals K, right? So this molarity cancels, put a 1 here for a placeholder. And so K equals 1 over, the traditional way to write this is put the molarity first, okay? I'm not gonna take off if you don't, but 1 over molarity times second. Okay.
So the traditional way is to put molarity first?
Uh-huh, but it's not a big deal. Okay. So for this case, when the overall order of the reaction was 2, overall order equals 2, that's what it looks like. And that's going to come into play in a second. I'm going to show you something.
And the S is seconds.
Yes. Okay. So we're going to do the same thing. This is a different problem. Okay. So what's the order of the reaction with respect to the first reactant? C6H5 into Cl. One. And then the second reactant, H2O, is there is an exponent there.
For H2O.
You see that?
On the bottom?
Oh, on the bottom.
Yeah.
Yeah, yeah. Look at the rate equation. Yeah.
Oh.
Yeah.
We're not looking at the balance part right now.
Yeah, we're not going to actually use this at all.
Oh.
Okay? It's there, but we don't need it to solve these problems. Okay?
0.
So it's 0. Okay. So what is the overall order of the reaction? 1. Right? We had 1 plus 0. And so our overall order is 1. Or first order. Okay? You can use either language. 1 first order. 2 second order. Whatever. Okay. So here, what's the unit of the rate constant? So let's do this again. Molarity over seconds is our rate unit. Okay? We're just filling in each of these parts in the equation. Okay? We have K. And then our units for concentration is molarity. Here it's to the 1 power, no exponents. This one, I'm not going to even write, okay, because it would be molarity to the 0 power, and that equals 1, right? It doesn't, the molarity units cancel too. Or not cancel, but molarity units are to the 0 power 2 and end up equaling 1, okay? So finally writing this out would be molarity over seconds times molarity. Both of these cancel, equals 1 over seconds. You don't even have molarity in the unit, the final unit.
But then how do we get the answer? Because we were not given the time.
You would be if,
Okay. But
yeah.
just in this example, we're not given the time.
Yeah, you'd be given the rate to fill in if you were doing this. But right now, I'm just showing you what the units of your K needs to be. Okay. So the overall order on this one was 1. Just a reminder. Okay. Skipping those first couple questions, like on those other ones that we did, we're just going to go ahead and go straight to overall order. What's the overall order of this reaction? Looking at the rate law.
2.
So you're adding up all your exponents. You have a 2 here,
Oh, 3.
and you have,
Or no, that's a subscript. So 4.
yes. Okay, so this bromate here has an unwritten 1 exponent. This bromide ion has an unwritten 1 exponent and 2. So 2 plus 1 plus 1. Okay, so what's the unit of this rate constant? So put the rate, molarity per second, equals K. Okay, and so no matter what, it's molarity. This one's to the 1 power. This goes to the 1 power. I'm just filling in for each of these. Molarity, molarity, molarity. This one is to the 2 power, right? And so overall, all of these molarities multiplied together are molarity to the 4th power, right? So we have m over seconds times molarity to the 4th power equals k, all right? And so how that cancels, right, is this m cancels and this 4 turns into a 3. You get 1 over... Okay, let's do it longhand. Okay, I'm gonna write it over to the right. Okay, so you have the m, and molarity to the 4th power would be seconds times molarity times molarity times molarity times molarity, right? And so only one of those molarities cancel, and so this equals m to the 3, right? So we started out with m to the 4 because there were 4 of them, and one of those cancels, and so you're left with m to the 3. Yes, that's okay. All right, m to the 3 times seconds. So that is that. Okay, so here the overall order, I'm going to call it OO just to shorthand it, was 4. Okay, so what I want you to see here is the rate constant is directly related to what the overall order is, okay? So here, the overall order was 4, and the rate constant has m to the 3rd power at the bottom, okay? Here, the overall order was 1. We technically have m to the 0 power at the bottom, okay? So 1 minus 1 is 0. It's not there. Here, we had an overall order of 2. 2 minus 1 is m to the 1 power at the bottom. Okay, so it's kind of a little trick for figuring out what that unit is quicker, is the overall order minus 1 is how many m's are at the bottom of the fraction in the denominator of the constant. Okay. Now here's a tricky one. What is the unit of the constant if the overall reaction order is 0?
Is this the one with the chart, or is that a separate question?
This is a completely separate question.
Okay.
Just what is the overall unit of the constant if the overall reaction order is 0?
Nothing.
So in the denominator, we're putting, you have seconds, right? And then times the order, well, I don't even know what I'm writing here. Okay, order minus, sorry, let me redo this. Okay. 1 over, you have seconds, and then you have m to the order minus 1, basically. You can follow the same thing. So 1 over seconds times m to the, well, order is 0, minus 1 is, what's 0 minus 1? Negative 1, right? So s times m to the negative 1. Now technically, how you rewrite that, when something is to the negative power and it's in the denominator, you switch sides. It moves to the numerator. If something is to the negative power and it's in the denominator, it's actually to the positive power if it's in the numerator. And so this would be another way to write that. Okay. If you want to keep it in the denominator, I'll understand what you mean, and you can do that. But technically, that's the better way to write it.
Okay, Kim, do you mind backing up one step back?
Okay.
We're talking about how you're getting that number again, like
the overall order or?
The overall order minus 1.
Okay, so so the unit of the constant is, if we, essentially it's because molarity is in the numerator of the constant, it's always going to cancel somehow with all of the molarities and the concentration that you're dividing by, right? So one of those is going to cancel always. And so if you have an order of 4 and one of them cancels, then 3 of them are still in the denominator. Does that make sense?
Yes.
Is that what you needed me to explain?
Yes. I don't
Okay.
It's not like sticking in my head. That makes sense. It's
Okay.
not really making- But I just don't know where this is like fitting into that. But maybe I'm.
Because they will need to be able to say what the units of the constant are. Because you're going to actually calculate what the constant is in a little bit. Okay. So now how do we actually determine what those reaction orders are? Okay, so everything up to now, I've given you the reaction order and you're telling me some things based off of that, but how do we find out what the reaction orders are? And that's by having these experiments, okay? So this is the same reaction and they did 3 trials of it and they're changing one thing at a time. Because if you change 2 things, you don't learn much about either thing because there's too many things changing. You don't know whether the reaction rate doubled, tripled, etc. because of the first reaction or the second reactant, okay? And so between trial 1 and 2 in this one, they are keeping the concentration of the nitric oxide the same, right? It's both 0.05 molar, but they're doubling what the concentration is of the hydrogen, okay? So they're just changing one thing so they can learn what happens to the reaction rate if I just change hydrogen. How does hydrogen affecting the reaction rate? Okay, so then they do a 3rd trial and they keep the hydrogen the same as what it was in trial 1 and they double the nitric oxide. And in that one they're learning what happens to the reaction rate if I just change nitric oxide. How is nitric oxide affecting the rate of the reaction? Okay? So,
And it's asking what are the orders?
yeah, we're going to just figure out the reaction orders of each of these. So, okay, so between trial 1 and 2, the hydrogen is the first one we're looking at. Okay, it doubles. Okay, so the change in hydrogen, it increases by a factor of 2. Okay, so here we're just dividing one by the other and putting what that answer is, right? 0.04 divided by 0.02, answer is 2. It doubled. Okay, now when I look at the instantaneous rate between those two, it also doubled, right? So my X is in here, and here I'm on the right. So here is the concentration change, and here's the rate change. Okay, so concentration doubled, rate doubled. So 2 to the what power equals 2? 1. So my H2 order is 1.
Okay, where'd you get the 1?
So
First one, 2,
where I filled it in, hold on, let me change this to a laser pointer.
Wait 1 second.
Okay, so the concentration factor change was 2, it doubled. The reaction rate factor change was 2, it doubled. And so what I'm figuring is what exponent goes here, which is what the order is. It's the same exponent that will go here. Okay? So 2 to the what power equals 2? 1, right?
Okay. 2 to the 1 power
Is 2.
equals 2. Okay. I need
Yes.
to write that down. Two.
Okay, so let's do the other one. Okay, so now we're looking at trial 1 and 3 because this is the important thing. How you're picking which trials is you're looking at the trials where one thing doesn't change and one thing does. Okay, they might not be in this perfect 1 and 2, 1 and then 1 and 3 situation. They might be different. Okay, but here we have this is the same. Okay, and the nitric oxide is different. Okay, so what happened to the nitric oxide concentration? Okay. And what happened to the reaction rate difference? By a factor of?
I have no idea.
So divide. Did anybody bring a calculator?
Can't you just like subtract that number by that number?
It's not subtraction. You have to divide.
You have to divide
Because we're doing
this
exponents.
together.
Okay? We're figuring out 2 to the what power equals how much this rate changed. So how many?
125.
You divided the wrong things. So make sure you're dividing the big number by the small number. 4? Did you do trial 1 and 3, not 2 and 3? Yeah. Make sure you're dividing the right trials. 8. You should end up with a nice, very close to integer number. Okay? So 2 to the what power equals 8?
2 to what?
So 2 times 2, how many times is?
2 to the 4th.
No, that's 2 times 4.
Which is 8.
So think of 2 times 2 is 4 times 2 is 8. So how many times do we multiply 2 by itself?
3.
3. Okay.
So 2 times
This
3 is
exponent
8?
is not the same as multiplication.
Yeah.
What?
I mean, you do multiplication, but it's not like linear multiplication.
It's exponents. So 2 to the 3rd power.
It's like multiplying it by itself
So-
by that number.
So 2 to the 3 equals 2 times 2 times 2. You multiply it times 3.
Yeah.
All right? 2 to the 2 equals 2 times 2.
Okay.
2 to the 1 equals 2. Is that making sense now? Okay. Okay. There's a number of 2's you have in the multiplication. All right. So that order of the nitric oxide is 3. What is the overall order of the reaction? 4. Okay. Okay. Let's see if you can do this one on your own.
It's too early.
Too early.
So it doesn't matter which one we start off with first? Does it matter if I start with XE?
No?
It doesn't.
No?
That's
As long as you pick the right trials. So make sure that the first set of trials you pick 2 where one of them changes and the other one does not. And you're not looking at the rate, you're looking at the concentration because the rate's going to be different across all of them.
huh.
So,
Start the first trial. Look at the second one. There's different change. So you're gonna figure this. What happens to
Okay, so I'm gonna start with trial 1 and 2, right? The ones that are the same are the fluorine concentrations, and the xenon concentrations change. So I'm gonna focus on the xenon. The xenon concentrations, it doubles, okay? So you're taking 0.3 divided by 0.15, and you get 2, right? So xenon, it doubles. Okay. And then the rate change, okay, I'm going to take the high rate divided by the small rate, so 0.0224, sorry, 224 divided by 0.00556, and you get 4. Okay, so the rate quadrupled. And so then, to get what the order is, you say, how many 2's do I have to have in here in a multiplication problem to get 4, or 2 to the what power equals 4, okay? And so my x equals 2. 2 to the 2 power, 2 times 2 equals 4. So then for fluorine, we're going to do this, oh, not FL, just F. Okay, we're going to do the same thing as F2, but the trials we're going to use are the ones where xenon stays the same. So that's going to be trial 1 and trial 3, okay? And so what happens to fluorine between those trials? We have 0.3 divided by 0.15, and that's going to be 2 again. The concentration change in this one was also 2. And that's done on purpose. Like, this is the part that the experimenter is controlling. They're like, what happens when I double the concentration of just one of these? Okay?
So
The answer for the concentration is 2?
Yes, the concentration, yeah, the change in the concentration is 2. It doubled. Okay? Then if I look at the rate, right? So I'm going to take 0.0112 divided by 0.0056, and for that one the rate also doubled. Okay, it equals 2. So 2 to the what power equals 2 is our y equals 1. Okay, and that this x and y are our orders for the rate equation.
So the first one, x was 2. And this one, y.
Yeah. It doesn't matter what you're calling them, x, y, or to say order equals 2. I'm just I put the x in there because I've made it a variable right here.
Yeah, yeah.
This would be y. Okay.
Okay, but the answer is
2.
2.
Yes. Okay. So now we're going to fill in the rest of the equation. Okay? Because we need to find the rate constant. Okay? Like, rate constants, typically you're given those in an equation. That's what a constant is. Okay? But for these reaction rates, the constant changes depending on temperature and stuff. Okay? But the way this rate constant will work, though, is if we are changing up the concentrations, as long as we have the same reaction and the same temperature, once we fill in that rate constant, we can put in any concentrations we want and figure out what the rate of the reaction is going to be. Okay? So, that's a reminder of what our full equation is. Rate equals K, and it's going to be concentration of NO, right? And we previously figured out what our orders were, okay? So this one we're skipping some steps because we just did it two problems ago. So what was our order for nitric oxide?
3.
So NO to the 3 power, and then H2 to the 1. Okay?
Wait, I thought we don't put the 1.
Yeah, you don't have to. I'm just writing it out for. Yeah. Okay. Yeah. Okay, you don't have to. Okay, so we have a rate equals a constant times and concentration of nitric oxide to the 3rd power times a concentration of hydrogen to the 1st power. So if we want to solve for one thing, we've got to fill in numbers for everything else. And luckily for us, we have all these numbers in all these trials. Okay? You have in each of them, we have 3 different sets of them. We have a concentration, and a rate. And those are the 3 things that we need to fill in. So at this point, once you have the orders and you're trying to figure out the rate constant, pick one of the trials and fill in the numbers.
Does it matter which one? Or do we...
It doesn't matter which one. Just pick the one that looks like it might give you the easiest numbers. Okay? So for me, if I'm picking one, I'm going to pick trial 3 because it has a 0.1, and that anytime you have just tens there, it gives you an easier number. Okay, but honestly, it doesn't matter. All of them would give you the same answer. Okay, so I'm going to pick trial 3. And so I'm just going to fill in the numbers. 1.072 molarity per second equals, K is what I'm solving for, so it's going to be left on its own. Okay, my concentration of NO in trial 3 is 0.100. Trial 3.
Oh, I see.
Trial 3. Yeah. 100 molar. And do not forget your exponents. It's going to be to the 3rd power. And then my concentration of my hydrogen is 0.020 molar. And I don't need an exponent on this one because it's 1. Okay? So, then you just start solving for K. So you have 1.072 molarity per second equals K times, when you multiply the concentrations, and don't forget your exponents when you're multiplying it. So you're going to do 0.1 to the 3rd power on this, right? And then times 0.02. You're going to get 0.
So you're just multiplying across? Or not dividing?
1, 2, 3. I'm just multiplying what's after the K right now. Just putting it all together. Okay, so when you multiply 0.1 times 0.1 times 0.1, you can use your exponent function in your calculator, but that's what you're doing. And then all of that times 0.02, you end up with 0.00002. And then don't forget your units of your molarity you also multiplied. So you have molarity times 1, 2, 3, and then 1 more for the hydrogen concentration molarity. Okay, so it should be molarity to the 4th power. Okay, so now you can divide 1.072 divided by 0.00002 molarity to the 4th power. Okay, and you'll get 53,600 1 times 1 over you have molarity to the third power of the 3 times S. Okay. Then last thing, as always, you're going to look at significant figures. Okay. And we have 2 significant figures in several spots here, but 2 significant figures, and so you're going to get 54,000. So you can write it this way, 1 over molarity to the third power times S, or you can do 54,000 divided by molarity to the third power times S. Whichever way you want to write it.
It makes sense when you do it.
Okay.
That's good.
All right. So let's do another one. Okay, we're gonna same thing, and we already found the orders in the previous problem. Okay, I'm going to tell you this: you're going to have one 5-point question on the exam that is this from beginning to end. Okay, so it's just all of it. It's find out. I'm just going to give you the trials, and you're going to have to find the reaction orders first, and then the rate equation, including the rate constant. Okay, now there's only one question like that. Every single other question, I think there might be 1 2-point question, but every other question on the exam besides that is a 1-point question for chapter 15. So there's just one long one. Okay.
So what we just figured out, are we doing another problem on the same, are we continuing on?
We are doing another problem, but we already did the first part of it. This is like using the table number 2 on your sheet. We already did the reaction orders on it. We're just doing the second half and finding the rate constant now. Okay, so 2 problems ago, we found the reaction orders for this table. Okay, now we're going to take those and find the rate constant. Okay, I'll do this one with you again. Okay, so we're going to fill it in. We have rate equals K.
This is still part of the same problem.
No, it's just the second table that we're working on now.
Xenon squared and F2. Okay, and so now you already found the reaction orders. We're just filling it in. Which one did I use here? See, this is going to be a fun exam for me to grade. I'm glad there's only one of these because you can pick 3 different ways to calculate it. So, yeah.
Yeah. So you're just doing
Okay, so which one? I'm doing trial 2. Just, it looked, because of point 3, it looked better to me. But, okay, so
I like the look of 0.3 too.
yeah, okay, so the rate is 0.0224 molarity per second, okay, equals K. My concentration of xenon, remember I'm looking at trial 2, is 0.3 molar. And don't forget your exponents. And the concentration of fluorine is 0.15 molar. And exponent is 1 there, so we don't need 1. Just rewriting this and solving the right side first. So 0.3 squared times 0.15, you get 0.135 molarity to the third power. Okay, and then we'll divide both sides by that, 0.0135 0.35. Okay. And so you end up with 1.66 divided by molarity squared times seconds.
Oh yeah, it cancels out one of them.
Well, yeah, cancel out one of the molarities.
Okay.
Equals K. As this one does have 3 significant figures, so it's already in the correct number of significant figures.
That one wasn't too hard.
So like this whole thing, it's a lot, but if you understand each step, each individual step isn't awful. It is just a lot to do all of it. I'll recognize it. And that's why it's only like one problem where you're doing all of this once on the exam. Okay. All right. Let's do one from beginning to end. Okay.
Oh, wait, it's not in the table.
Huh? You have the table.
I know, but I'm saying it's just a different.
Yeah, it's a different format. I copied and pasted it from a set of practice problems online. Okay, so I'm gonna let y'all work on this because you have learned each part and we've practiced each part multiple times. Okay?
Totally.
So just take it one part at a time. Let's do the reaction orders first. And then once you've got those, you can work on the rate equation.
Okay. We don't know what. Okay. So since we don't.
Yeah, it doesn't matter what A and B are. It's just telling you what matters is their concentration. I don't know if that's what you're about to ask.
Yeah.
Okay.
That's it.
It doesn't. Yeah, it doesn't matter what they are.
Okay.
I could call them anything.
Ooh.
So you're just like monitoring three completely impartial.
So.
So, okay, so the original 4 was your concentration, so 4 to the what power equals 4? Multiplying 4 by itself, how many times do you multiply 4 with to get 4? Just one. Right? Or, yeah, so 4 to the 1 power. So 1, which your reaction order will be. And so, what I would do here is just go ahead and write out what your B is. Do this upside down. And it's a 1 there, or you can just not write anything right? Okay, and so now, go find the trial where B stays the same, which you already did, and A is different. So now you're looking at the number A, and 1 and 3, and you're going to ignore trial 2. Okay? And do the same thing. So what biggest number divided by smallest number between trial 1 and 3? Average. Okay, so that's your concentration change, right? Okay. So you divide it by 17 divided by 4. You're going to do the same thing, like 1.88 847 to get the factor that the rate changes by. Okay, so now you have to determine what exponent needs to go here to get that. So 4 to the what power equals 4. 4 times 4 equals 4. That's what you're doing. Every time you have an exponent, you're multiplying the number by itself. So, oh, I'm sorry. So 4 to the 2 is 4 times 4. Just 1. Okay, so that is your reaction order for B. So what I would do still is write it out because you're going to use it later. Is do the 1 power, or don't write it, but use it by the 1 you're trying to find yourself. You have done that. What the reaction order. Okay, or when the end, like it's asking this, determine the order of each reactant, B equals okay, so now you're doing the same thing for A. Find the reaction for B doesn't change, but A does. And divide the biggest one by the smallest one. And the reaction of the biggest one by the smallest one. It's yeah, it's really close, yeah.
So if you are dividing these, you might not end up exactly an integer, but you should be really close, and it's okay to round.
Yeah, I got for B, I got 4 divided 0.117 divided by 0.470. Is that right?
No, because you always divide the biggest one by the smallest one. So yeah, if you're not even close to an integer, you've done something wrong.
Right. I just didn't.
Maybe you just said the wrong thing, but you actually did it right.
117. Like here,
So-
we got 4 again. I put in the right way.
Okay, yes,
Yeah,
that is
so
very, very close to 4, and Yeah, that's basically what I was
So-
talking about. So that would be 4.
So my overall is 8 then. Because I got 4 for A and then 4 for B as well.
Okay. So did it, so 4 to the, yeah, okay, so for A, where's your math for A? What'd you do?
I just divided.
Okay, so for A, you did,
I divided, I think I did these two numbers, which got me 4.
it shouldn't be more. Okay, so you have 0.72 divided by 0.36, so that's 2. Then,
Oh, I did these two, and it gave me 4.
so this is for B, that's B changing. Correct, trial 1 and 2? Okay, so that is 0.72 divided by 0.18 is 4. 0.18 divided by 0.47 is also 4. So, but what you are determining is the exponent. So 4 to the what power equals 4? Your factor change here is 4, your factor change here is also 4.
So just 1
Yeah.
for just this.
For B, yeah.
But why not for 4? Or why not for A? Why
So
still
let's
not
look at
4?
A. Okay, so here you have 0.72 divided by 0.36, so that's 2. Here, 0.18 divided by 0.117 is 4. So what you're actually determining here is 2 to the what equals 4. Okay, this is your factor change in concentration of A, right? This is your rate change. Factor of the rate change. Okay? So 2 to the what power equals 4.
So for that.
So what you're saying with the next one, 2 times 2 times 2 times 2, that's what 2 to the 4 looks like.
Right.
So that equals 4?
No. It's 2.
Yeah. So it should be 2.
So not 4. Got it.
Alright, I'm gonna do the first part. Okay, so to get the reaction order, I'm gonna look at the trials and see for one of the concentrations, they need to be kept the same, the other ones, they're different. Alright, so between trial 1 and 2, the A is kept the same and the B changes. So I'm solving things for B right now. Okay, I'm taking the highest concentration divided by the lowest concentration, 0.72 divided by 0.18, and I get 4, right? That is the factor that the concentration of B was changed by, right? It was quadrupled, okay? I'm going to look at the rates for the same ones, okay? So I have 0.188 or 1.88 divided by 0.47, okay? And that equals 4, okay? That is the factor by which the rate changed, all right? So the concentration quadrupled and the rate quadrupled, okay? And then I'm going to take these and figure out my x. So 4 to the x power equals 4. How many times do I multiply 4 by itself to get 4? Okay? It's just 1, right? Not 4 times 4 times 4 times 4, right? It's 1. So my b to the x, right, for my rate equation is going to be 1, okay? And for A, do the same thing. I'm going to change colors here. But I'm changing which trials I'm using. Now I'm going to use trial 1 and 3 because B is kept the same and only A changes. gonna take the largest one by the smallest one. So I'd do 0.72 divided by 0.36, and I'm gonna get 2. Okay, so we doubled the concentration of reactant A. For the rate, I'm going to take 0.47 divided by 0.117, and I'm going to get 4. It's actually 4.01 something, very, very close to 4, right? You should be getting an integer value for these numbers, okay? Because it's always going to be an exponent value. So 2 to the x equals 4, right? It wouldn't be decimal places. Okay, so my x here is going to be 2 because it's 2 times 2. There's 2 2's that equal 4. Okay, and so for A is 2. Okay, so for my order then is A is 2 and B is 1. What is my overall order if A is 2 and B is 1? 3, right? 2 plus 1. So my overall order is 3. Okay, so now we know the orders, and you can fill in the rate equation to determine the rate expression for the reaction. Okay, so if you haven't started working on that, work on that.
I did, I don't know if my answer is right. So don't
Okay. Okay, so pick a trial, whichever trial you think is the easiest to plug in the numbers for, and plug your rate, a concentration B and a concentration A, into the equation. And then you fill in the X and the Y based on what you just figured out. You done?
Which one is the exponent button? The exponent, which one is the exponent button? That? No. X to the Y.
And what's the units?
1 over seconds times k.
M to the second, right? Yeah.
My m is canceled. Or wait, huh?
Yeah, your M stays there.
Okay, so it's 1 times s, or 1 divided by s times m equals
M squared.
squared.
Yeah, okay.
Ah.
Okay, so let's just, so all we do once we've found the orders is we just fill in the numbers for the rate equation, right? And pick a trial. I initially picked 1, but Ethan pointed out that like 2 actually looks kind of good because you have the same numbers here. Any of them are fine, okay? But let's do 2, okay? So my rate is 1.88, okay? And just a reminder, our equation is rate equals k x b to the y. That's where I'm pulling these numbers from, okay? My units is molarity per second when I do the rate equals k. My concentration of A for this trial that I've picked is 0.72 molar, and my order for this was 2, right?
Yep.
So that's what I determined in part A of this. Okay, my concentration of B is also 0.72 molar, and my order for that was 1 based on what we determined in part A. Okay, so like part C in this would be basically this right here, but filling in the x and the y, so putting in a 2 and a 1 here. We kind of just skip that and just give me the whole rate equation with the k. Okay. Okay, so once I've done that, I have 1.88 molarity per second equals k, and this one's a nice one. It's not like nice numbers, but it's an easy one to plug into your calculator because it's 0.72 to the third power, because 0.72 to the second power here, and then you multiply 0.72 again. So it's 0.72 times 0.72 times 0.72. Or you can put 0.72 to the third power if you know how to use your calculator. Okay, so 0.72, x to the y, 3, and you get 0.373. And my units there are molarity cubed because I had 2 here and 1 here. Okay, so then I divide the rate by 0.373 molarity to the third power. Okay, so one of those molars is going to cancel, right? Oops, not that. And it's going to end up with molarity squared when you do that. And so the final answer, and it's okay if you have a rounding error, and my answer here is from me doing trial 1, and I think you got 5.02, rounding error is fine. 5.04, and my units are going to be over molarity squared times seconds. Times seconds. Because my seconds remain from my rate. Okay? This is the hardest part of the chapter. Luckily, it's unusual that the second half of a chapter is easier than the first half, but it is in this chapter. It's way easier. I'm going to go through it so fast next week. So we're going to get more time to practice this next week in tutoring. I mean, it's good news, bad news. It's not super fun, but you get more practice on it, so hopefully it won't be as bad on the exam. Okay? All right. Bye, Jackson.
Bye, Jackson. Love you.
See you tomorrow.
Clap, clap.